Cancer medicine has made huge advancements with the discovery of key driver mutations, genetic testing, and sequencing of tumor biopsies, leading to overall earlier detection and better prognosis. But at the same time, some aspects have not advanced as much as we would like. A quick search of the Canadian Cancer Society website will tell you that in most cases, the primary treatment options are still surgery and non-specific chemotherapies and radiation. But this is not for a lack of research. We are learning more and more every day about the processes occurring and leading to the transformation of cancer from normal cells. But these discoveries have not been translating to clinical successes. One of the major hurdles is the identification of druggable targets that are lethal to only the cancer cells. This is where my research comes in. Our lab uses high-throughput techniques to identify genetic interactions that are selectively lethal to cancer cells. My project focuses on polo-like kinase 1, or PLK1, a gene that shows overexpression in many cancers across different tissue types and may play a role in the transformation of cancer. There's mounting evidence that inhibiting PLK1 selectively kills cancer cells, and several inhibitors have made it to clinical trials. But unfortunately, the off-target effects cause these to ultimately fail. My work proposes to use synthetic doses lethality to identify alternate, hopefully more effective and less toxic targets within the context of PLK1 overexpression. Cancers can become dependent on the mutations that arise from the transformation, such as PLK1 overexpression, and synthetic doses lethality proposes that this should cause vulnerabilities, where the inhibition or where a second normally non-lethal mutation becomes lethal in the context of that cancerous mutation. Specifically, inhibiting a second gene would be lethal only when PLK1 is overexpressed and not in normal cells where PLK1 levels are normal. In order to identify such genes, we systematically inhibit every gene in normal and high PLK1 cancer cells, and then compare the viability using microarray technology. I've already completed this for PLK1, and my work is now focusing on using chemical inhibitors and gene modification techniques to validate and characterize the promising targets. Any targets that pass this validation will be tested in animal models and hopefully clinical trials. Cancer is not a single disease with a single cure, but rather an array of different mutations with different vulnerabilities, which we hope to exploit. With personalized medicine moving towards treatments based on the genetic mutations of cancer rather than the tissue of origin, cancer medicine will continue to improve, getting us from point A to point B. Thank you.